Hello everyone, welcome to Devjit Decodes. In today's video, we are going to see the topic PNP, NP complete and NP hard. What are these things? Let us have a first quick brief about it. Suppose say you have a huge password. Say a system is having a huge password. Say suppose the length of the password is 100 say characters. 100 characters. So if the length of the password is 100 character, can you imagine like breaking this password, how tough or difficult it can be? Like for an example, if it is 100 character, then say there are blank 1, 2, 3, 4 like that up to 100, right? So here it can be any digit between 0 to 9. It can be any digit between 0 to 9. It can be 0 to 9, right? Here also 0 to 9. Here also 0 to 9. 0 to 9, right? So same for 100. So how many possibilities? There are 10 possibilities. 10 numbers can be there. There can be any numbers from 0 to 9, any numbers from 0 to 9. So up to which? Up to the 100. So what is the total time taken? That would be 10 to the power 100. That is 10 to the power 100. So if you can imagine, if we apply the brute force technique, or if we kind of try to solve it, how much time can it take? Right? It is taking a humongous amount of time to do this thing, to kind of break a huge password. But suppose someone has given you the correct password. Someone has said, bhai, this is the password, say 572911130 like that, a 100-digit password someone has given you. Now, how much time will it take to verify whether this password is correct or wrong? Just think about it. It will just take few seconds. It will just take few seconds to verify whether this password is true or wrong. So there are, what we are trying to say, what we are trying to build up here, there are problems which can take huge amount of time to get solved, but can be verified in very less amount of time. Why I am talking about this? I am coming one by one. But before that, let us talk about the things we have already done. That is, we have made almost 50 plus videos in this playlist, and you can check that we have done several sorting, searching, graphs and all these things. So I have listed down few names of those algorithms. Suppose a bubble sort. It is taking order of n square. Selection sort, it was taking order of n square. Insertion sort, in best case it was order of n, but in worst case it was order of n square. Similarly, quick sort, in best case it was order of n log n, but in worst case it was order of n square. Merge sort was best, worst, average, all were n log n. Right? Now if you can check, though this thing, say bubble sort, is not that relevant in terms of merge sort, it is really big. The value is really big, n squared is really bigger than n log n. But we are still considering the bubble sort. Why? Because if you can check, all these algorithms can be solved in polynomial time. Polynomial time. This is polynomial, this is polynomial, this is polynomial, this is polynomial. All these are polynomial time. This can be solved in polynomial time as well as verified in polynomial time. So even though one particular sorting is taking way much more than another particular sorting, but still we are considering this thing because at least this thing is getting solved in polynomial time, right? So this is the main logic behind it. So whatever the say algorithms you have done so far, majority of them, a huge bulk of them is belonging to this P. What is this P? P is nothing but polynomial. P stands for polynomial time. That is, if you can check, all this sorting are done in polynomial time, and verification also can be done in polynomial time. Now if you check the searching part, linear search was taking n, order of n, binary was taking order of log n. So log n is again really smaller than this particular n, but still we are considering linear search, obviously, because obviously this bubble sort, linear search, these have some other significance as well. I'm not kind of throwing it out, but for the time being I'm just saying that this linear search can be considered because at least it is doing in polynomial time. If you can check, this is order of n, right? N to the power 1, something like that, right? Now if you can again check the graph, if you can check Dijkstra, or say it is taking say e log v, or say v square in worst case or something like that, okay, e log v or v square. Bellman-Ford is I think taking order of e into v, or say in case of worst case again it can be a complete graph, it can be order of v cube as well. Now, if Floyd Warshall, it is taking order of V cube. So even if these things are taking V cube, it's a huge value. It's a huge value. But still we are considering it because at least it is doing it in polynomial time. So these things, whatever we have done so far, those algorithms are actually polynomial time solvable as well as verifiable. Now we will be seeing what is the concept of NP, NP complete and NP hard. Okay, now let's just see what is the definition of actually P. We have talked about the P thing just now. That is saying that problems that can be solved in polynomial time and the verification is also quick. That is, the verification can be done in polynomial time as well. That is, say the time complexity can be n square, n cube and so on, right? So if you can see, this is what we have just talked about. And one more thing is written over here, that is improvement can be done. What is the meaning of improvement can be done? Say in polynomial time, for an example, let's take the concept of merge sort and say bubble sort. So initially, say bubble sort was there, just try to assume initially there was a sorting algorithm that was taking order of n square time. So we made sure that we reduce that to order of n log n time and the complexity is reduced. So it is staying in the polynomial, but there can be some improvement. That is the meaning of it, that improvement can be done. Even if it is staying inside this thing, somehow if someday discovers a sorting algorithm that runs in worst case order of n time, that might also be a possibility, right? Right now, whenever we are thinking like this, that how can it be done in order of n times? Might be someday we thought like, how can it be done in order of n log n times? But it is doable, right? So we need to keep on thinking. We need to keep on the scope for improvement. So that's what it is saying, that problems that can be solved in polynomial time, verification is also quick as well as there can be some improvement with say daily basis, right? We can try, keep on trying. Now let us see, let us come to this concept of NP. This is a very new concept. Let us understand what is this. If you think that P stands for polynomial, the by default thing that comes in our mind whenever we hear the word NP, that is non-polynomial. But it is not non-polynomial, it is actually non-deterministic polynomial, right? NP stands for non-deterministic polynomial. It is saying that these particular problems, say these particular algorithms, whichever is belonging to NP class, those are easy to verify, not necessarily easy to solve. That is, it can be, might be verified, it is written, problems whose solution can be verified in polynomial time. That is, given a solution, you can verify whether that solution is correct or wrong, seeing that solution in say very little time, in say polynomial time, using a deterministic algorithm. You can do it. But to find the necessary solution, that is not at all easy to find. If given a solution, you can verify. But to find the necessary solution, it not necessarily easy. That's what it is trying to make. So what can be the say example? Say Sudoku or say puzzle. Just think of a puzzle. Say there is a puzzle, say small fruit box. There is a 100 x 100 puzzle. Now they are asking you to solve that puzzle. There is an image puzzle. You need to form an image. I hope you have seen those things. Now if they are asking you to form the image, you might take, it is 100 x 100 or 1000 x 1000 small blocks. You might take a day or 2 days or 3 days to complete that thing. But if someone has done that, if you can see, if you just look like this and you can see, okay, this is correct. Because if one eye is missing, suppose there is a diagram and there is a puzzle block you are trying to solve and there is a person, you are trying to make a person using those blocks. And if suppose the eye is disturbed, the eye is in place of nose, you can check and you can say, okay, this is wrong, that is wrong. Or say if it is perfectly fine, okay, that is perfect. So in that case, what it is saying, that easy to verify, that can be verified easily. Or say Sudoku. In case of Sudoku, what do? We play Sudoku, we try to match the row and column and all these things. So if there is a say 100 x 100 Sudoku or say 10 x 10 Sudoku, huge Sudoku is there. In that case, it is not at all easy to solve. But if someone is giving you the solution of the Sudoku, you might verify in say not that much great time. You can verify in a small time. That is the concept of NP. So you can see we have just talked about the real life scenarios, but in the last video, just the last video, we have talked about TSP. What is TSP? TSP is traveling salesman problem. I have talked about in the last video. If you haven't checked it, kindly check it out. So we have talked about TSP and we have seen TSP, if we apply brute force, it was taking n factorial time. Now TSP, if we apply even dynamic, it is taking n square into 2 to the power n time. So there is still an exponential part left. So this TSP surely belongs, because you cannot solve it using, say, the polynomial time. So this TSP belongs to this NP class. This particular algorithm belongs to this NP class. Right? Now inside this NP, so if you can check, if you want to really understand that what is the relation between P and NP, is P equal to NP? This is the first question. This is a $1 million question. If P equals to NP, if you have seen this particular two definition, you might right now understand that P is nothing but a subset of NP. So till now the diagram might look like this. This is P, this is NP. Suppose you can think like that, right? Now there are two more variations of this NP. One is called NP complete, another is called NP hard. That is non-deterministic polynomial complete and non-deterministic polynomial hard. What is the meaning of NP complete? It is saying that this particular set of problems belongs to NP because these are easily verifiable. We can easily verify NP complete problems as well. But it is as hard as any problem in NP. What is the meaning? I am breaking it down. So this complete definition is, NP complete definition is, these problems are as hard as any problem in NP. That is, this NP complete belongs to this NP, but it belongs to that certain part where those are the hardest NP problems. Because inside this NP, apart from this P, I am just removing this part. You can check this particular thing, right? If you want to check this particular thing, there might be infinite, say there might be, for the time being, say there might be thousands of problems. So if there are thousands of problems, there might be 20 problems that is really difficult. So this particular 20 problems belongs to this NP complete. It is saying that it belongs to NP because these 20 problems are like, easily verifiable, but these are really difficult. Say if there are 1,000 problems, all the 1,000 problems difficulty will not be same, even though they are in NP, but all the 1,000 problems difficulty might not be the same. Right? Let's take one example so that you can understand in better way. For an example, say you are taking, say I am taking a class in my institution. So say everyone has cracked one particular examination to come here. Any examination. Say suppose after JEE mains they have come to some university, some college. A professor is taking the class. In that case, what is the scenario? If a professor is taking the class, all the students might have cleared the same exam, but their things, say their understanding purpose, their questioning purpose are not same or not similar, right? So if a professor can solve the doubt of the most brilliant student, say there is one student who is really hard for the professor, that he is asking questions and questions and questions. If a professor can solve the doubts of that brilliant question, it might be the case that that professor can solve the doubts of all the other questions, all the other students, right? This is kind of that, because it is saying that it belongs, the students belongs to this particular part, all the students, all the 1,000 students, but there are 20 students who are really great, who are really tough to break, who are really asking some great questions, right? So the professor should answer them. If they can answer them properly to those students, the remaining 980 students can be answerable, because they are not asking that much of a tough question. You can think like that in your brain. So one such example of a real life problem is ACT problem. Okay, we'll be doing it. So then I'll be telling in rigorously that what this thing is. But for the time being, just try to understand what we have just talked about. This is the definition of NP complete. That is, it belongs to NP because it is easily verifiable, but it is as hard as any problem in NP. Simple. So if you want to really draw the diagram again right now, what can be the diagram? So there was P. Suppose, say, think like this. There is P. So those who are really from, say, I'm not asking you to think completely like that. That might sound stupid, but still, if these hard problems are there, let us say the hard problems are in the, we are putting it in the right part. So if it is P and if this remaining part is NP, then the NP complete might be here. NP complete might be here because it belongs to NP. It is saying, so it is inside NP, but it is as hard as any problem in NP. Suppose the hard problems are in the right side. You can think like that. So NP complete is here. Okay, now let us see the last one, that is NP hard. What it is saying, problems at least as hard as NP complete may not be verifiable, may not be in NP. That is, NP hard, it is saying that NP complete was saying what? That the problems was as hard as NP. And here it is saying the problems at least as hard as NP complete. So this NP hard is like what? Between that NP complete, between the chosen 20 students, there might be 3 to 4 students who are really brilliant. This out of 1,000 students, these 20 were really brilliant, and there is say 2 to 4 students who are really brilliant. Like, so like that, problems at least as hard as NP complete may not be verifiable. That is, for an example, say this NP complete was saying it is belonging to NP because easily verifiable. NP, again, that can be verifiable. Those solutions can be verified. But here it is saying it may not be verifiable. The NP hard problems solve, forget about it. Even it cannot be verifiable as well in polynomial time, right? So it is saying that it may not be in NP, right? For an example, say let us take an example. Say you are playing a chess. You are playing chess, right? In between you give a move. Say you kind of give a move using your queen. So in that case, suppose you have played only 4 to 5 moves. All the opponents have played only 4 to 5 moves. Now, if the fifth move you are playing your queen, can you tell whether this is a win move? Because you cannot tell, right? You can think just the game has started, you have taken 3-4 moves and you are giving the 5th move. You cannot directly say whether that is a win move. So in that case, that particular thing may not be verifiable. That is what it is saying. That's the definition of NP hard. Now, if you want to draw the entire diagram, Venn diagram of all these 4, how it should look like? I think it should look like this. This, then this is P, this is NP, this is NP complete, and this is NP hard. Now, if you can see all the definitions, P is a subset of NP, satisfied. NP complete as hard as NP, yes, and also easily verifiable. So it is belonging inside the NP. But in case of NP hard, may not be verifiable, so may not be in NP, so it is going outside as well. And some part are intersecting because problems at least as hard as NP complete. So as you can see, there are some problems which is as hard as NP complete, that is towards the NP hard. So this is the whole Venn diagram. Now if you really want to think, suppose what we are trying to do, we are trying to make sure this is P, this is NP. We are trying to make sure this P's boundary is getting enlarged. The researchers are trying to make sure, whoever is doing research in mathematics, computer science, they are trying to make sure this P is getting more and more boundary. If it is getting more and more in size, it can put some more algorithms inside it. That means some more algorithms which are currently in exponential time can be done in polynomial time. That is what. So someday it will be growing, and it might be a case someday P will be equal to NP. We are hoping for this. If this thing happens, what will happen? If this thing happens, in that case, the thing I have started with, there is a 1000-digit or say 100-digit password. That can be cracked easily. If you want to find a route, a really difficult, say traveling salesman, that can be easily done. Right? So this kind of stuffs can be done if P someday becomes NP. The research is going on and on. And this is a $1 million question again. Right? So just one question to you all before say summing it up. I have said that this traveling salesman problem belongs to NP. But is it NP complete or NP hard? What do you think? Just think about this thing. If you haven't seen the last video, go watch and get the idea. Then think whether it is NP complete and NP hard, and let me know in the comment section. Thank you for watching this video. Stay tuned for the next videos.